Hi everyone, welcome to this video on differential equations in physics. Specifically, this chapter is going to focus on RC circuits. So I've already done a video like this where we analyze a differential equation in physics. That was with the drag force. I believe it's on an inclined plane, so you can check out that video. It's in my channel. But this is going to be another example of how we can see the world in a differential equation. So what we're going to be looking at is the RC circuit. So this diagram right here, as convoluted and foreign as it may look, this is what looks like a circuit. And you can tell just based on the parts of the circuit. These lines right here, these lines all represent wires. This sort of long line, short line thing, this is a battery, and this epsilon right here represents the voltage of that battery. Voltage of battery. More specifically, the ideal voltage. This is the voltage that we expect to get out of that battery. It's the voltage printed on the label of the battery. And then this line right here that doesn't connect to anything. This is a switch. We can adjust this switch to point A or point B, and we'll be looking at how that switch affects this circuit. And this zigzag right here, this is a resistor. This resistor, a common example is a light bulb. That light bulb essentially resists, it essentially just resists current, I guess you could say. It drops the voltage that loops around this circuit, and I'll get to what that means later. And then we have a capacitor here. A capacitor is basically something that stores electric charge. And this circle with an A around here, this is what we use to measure the current that loops through these wires. And this circle with the VC and VR, this essentially measures the potential difference or voltage drop. So for simplicity's sake, we're just going to stick with calling this the voltage drop. Essentially, how much does the voltage from this terminal to this terminal, by the way, this is what's known as the positive and negative terminal across the resistor. This is also positive and negative. This is essentially saying what is the difference in electric potential as we go across the terminals of this resistor. And that was a lot of jargon just then, but it'll all make sense when we actually analyze the circuit. So at time t equals 0, the switch is closed at point A. So let's go ahead and visually represent that. So it closes at point A, meaning that we're going to just see a line across, we're just going to see a line that connects A and that dot right there. And you can kind of see now, if the switch closes at A, then this switch pretty much acts like a wire, and it pretty much completes the loop. This B right here, this stuff's irrelevant for right now. So you can see this loop right here, it's complete since we moved the switch to point A. But now, how does this affect how we look at the circuit? Well, let's go ahead and take a look at part A. So part A asks us to define a function for VR of t and VC of t. So VR of t, that's just the voltage drop across the resistor, and VC of t, that is the voltage steal of the capacitor. Pretty much, the capacitor takes electric potential from the battery, and it essentially causes a voltage drop. It's the same effect. But for VR and VC, they are functions of time. So in other words, we might need to use a differential equation. Hence the title, Differential Equations in Physics. Well, what is something that we can use to sort of determine this differential equation? Well, this is something called Kirchhoff's loop rule, which just states that delta V equals 0. Well, what is delta V? Well, delta V is the change in voltage across a loop, or the potential difference. So in essence, what's happening here is as you go through the positive terminal of the battery, you're going to lose some voltage from the resistor, and you're going to lose some voltage from the capacitor. And then at this point right here, you're effectively going to have 0 volts of electric potential. And then you go through this battery right here, and then you're going to gain that voltage back. So therefore, the change in potential across the loop is 0. But what is the change in potential across that loop? Well, you know that you're getting voltage from the battery, so epsilon, or EMF, that is definitely part of the voltage. And what does the voltage drop across the resistor? Well, we need to use something called Ohm's law. So Ohm's law states that VR, or the voltage drop across the resistor, is equal to the current I that goes through the resistor times the resistance, which is a property of the resistor itself. And then, since this is taking voltage from the battery, we put a minus sign here. And same goes for the capacitor. The capacitor is taking voltage from the battery, so we're going to say a minus sign here. But what is the voltage drop across a capacitor? Well, by definition of capacitance, capacitance is charge per unit volt. You can just rearrange that to find that the voltage drop across a capacitor is just the charge on the capacitor minus the capacitance, which is a property of the capacitor, minus Q over C, which is 0. So now what we're going to do is we're going to do some rearranging here. And I'm actually going to rearrange to isolate IR, and you'll see why. So IR is equal to epsilon minus Q over C. But what is I? Well, I is current, right? But current, what is current? That is the rate of charge flow. We're pretty much just how fast the charge flows through the circuit, how much charge is flowing through the circuit. So, therefore, what we say is I is the derivative of charge with respect to time. So essentially, this is an infinitesimally small change in charge over an infinitesimally small change in time. So, therefore, we can say that R times the derivative of charge with respect to time is equal to epsilon minus Q over C. But let's clean this up a little bit. Why don't we? So, what we're going to do is, yeah, okay, I know how you can do this. So what we're going to do is we're going to multiply both sides by C, because we see that we have this Q here, but it's being divided by a C. That looks pretty unfriendly. So what we're going to do is we're going to multiply both sides by C, as I just said. So RC times dQ over dt is equal to C times epsilon minus Q. And there's resistance times the capacitance times the current is equal to capacitance times epsilon naught, not epsilon naught, times the EMF minus the charge. Just to recap what each quantity means. And now we're going to perform something called the separation of variables. So separation of variables, what we're going to do is we're going to move everything with Q onto the side with dQ, but everything without Q onto its own side. In other words, what we're going to have is if we divided both sides by C epsilon minus Q, and then we moved everything else, what we're going to see is we're going to have 1 over C epsilon minus Q times dQ is equal to 1 over RC times dt. And you can try doing the algebra on your own. You will see that these are the same thing, just rearranged a little bit. So now, as you can see, we have a dQ and a dt, and they're just on their own sides. So what we can do is we can get rid of this dQ dt, we can get rid of the differential expression, and the way we do that is through an integral. So we're going to go ahead and put integral signs on both sides. And since this is with respect to time, our limits of integration are going to be from 0 to some variable t, which represents time. And for here, this is pretty much saying what is the lower limit is going to be whatever the charge on the capacitor is at time t equals 0. Well, the instant the switch closes at A, charge isn't going to just instantly flow into the capacitor. Well, it will, but not like at the change of time of 0. There's going to be some sort of change in time. So the initial charge on the capacitor is actually also 0. And the upper limit is just going to be some random variable q. So let's go ahead and take the integral on both sides. So we're going to need to incorporate an integral property here. So the integral of 1 over x minus, not x minus a. Let's say just some constant a minus x dx. This is equal to, you might be familiar with this 1 over form. You're going to see that there is an ln involved. It's going to be ln absolute value of a minus x plus c, but we're not done. And if you have covered the chain rule, essentially this does involve a reverse process of the chain rule, meaning that you're going to need to multiply, or really divide, by the derivative of this expression right here, or of the inside expression, which is going to be a minus x. So the derivative of this is -1. So if you divide by -1, you're going to see that this is negative ln of this inside function plus c. So let's go ahead and apply that here. This is just an integral property right here. You can try it, you can look it up on your own. It's just there, it's a fact. But yeah, if we go ahead and apply that to this expression right here, you're going to see that this is going to be negative ln, absolute value of c epsilon minus q, and this is going to be evaluated from 0 to q. This is going to be equal to, well, 1 over rc, this is a constant, so it's really just going to be 1 over rc times the integral from 0 to t of dt. Integral from 0 to t of dt, that's a really easy integral to take. It's actually it's literally just t. So it's going to be t over rc, just like that. Now, what about this stuff right here? It looks a little bit convoluted, but we're just going to stick with it, right? So what I'm going to do first of all is just move this ln to the other side. Not the ln, the negative to the other side. And we're just going to divide both sides by a -1. Or really, we can multiply by -1. It doesn't really matter. So ln of c epsilon minus q, and I'm actually going to drop the parentheses here because c epsilon minus q will always be positive in this context, is evaluated from 0 to q. This is negative t over rc. And now we're going to go ahead and apply the fundamental theorem of calculus onto this left-hand side right here. So the fundamental theorem of calculus states that you just need to plug in this minus when you plug in 0 for this. And when you do that, what happens is you see that this is ln c epsilon minus q minus ln of c epsilon minus 0. So we're just going to leave it as c epsilon. This is equal to negative t over rc. But then this looks a little bit unfriendly, right? However, we can apply a logarithmic property. So a logarithmic property is that the natural log of a minus the natural log of b, this is equal to the natural log of a over b. So if we apply that to here, we're going to see that this is going to be the natural log of c epsilon minus q over c epsilon. This is going to be equal to negative t over rc. And now how do we get rid of an ln? You just take e to the power of both sides. The e and the ln, they will cancel. So this is going to be equal to c epsilon minus q over c epsilon. Sorry, that was a really bad division thing. So c epsilon minus q over c epsilon. This is equal to e to the negative t over rc. And now all you have to do is just do some algebra. I'm going to shortcut the algebra, but you can try to get from here to here, or the final function, as you please. So the final function is going to be the charge as a function of time is equal to c epsilon times 1 minus e to the negative t over rc. But I lied when I said final function because it's not actually the final function. Because here's the thing, right? Although we have a function, we're looking for the voltage across the resistor and the voltage across the capacitor as a function of time. This is the charge across the capacitor. However, using these three formulas right here, we can actually get these two things right here. So let's go ahead and do that. So I'm going to go ahead, continue that right up here. So what about the current as a function of time? Well, current, the definition of current is the derivative of charge with respect to time. So by saying that this is equal to dq over dt, this is going to be equal to the derivative of c epsilon times 1 minus e to the negative t over rc. And therefore, what we can do is we can say that this is equal to d over dt c epsilon minus c epsilon e to the negative t over rc. And I just went ahead and distributed because now we can just use the sum and difference rule and all the rules with e, and then we'll just be able to solve for the derivative. So the derivative with respect to time of C epsilon is a constant, so that's going to be 0. And the derivative of this whole thing, you just bring whatever in front of t down in front of the e expression, and then just leave the e as is. So what this is going to be is negative C epsilon times negative 1 over RC, because that's what is theoretically in front of t, times e to the negative t over RC. And as you can see, this negative cancels and a c cancels as well. So then the current as a function of time is going to be epsilon over r e to the negative t over RC. And now it's just the home stretch from here. So let's go ahead and solve for the voltage drop across the resistor as a function of time. Well, we know that this is going to be I times R, right? So this is just going to be R times epsilon over R e to the negative t over RC. And therefore, the voltage drop across the resistor as a function of time, this is equal to epsilon e to the negative t over RC. And then the voltage drop across the capacitor. Now, the voltage drop across the capacitor is just smooth sailing from here as well, because we know that the voltage drop across the capacitor is the charge divided by the capacitance. So this is going to be equal to, as we know, Q over C. This is going to be equal to 1 over C times what we have for Q of T. This is going to be C epsilon 1 minus e to the negative t over RC. As you can, C, sorry, no pun intended. So, as you can see, the capacitances will cancel out. So the result is the voltage across the capacitor as a function of time is epsilon times 1 minus e to the negative t over RC. So these are all the functions that we need, that we really need to know. Like, we have the formulas, but let's try to make some sense of this. So basically, here's what's happening. So this 1 minus e to the negative t over RC, if we were to represent this graphically, this would look, the charge as a function of time would look something like this. It would look like a concave down increasing curve. Now, why is that? Well, you can just go ahead and do the algebraic transformations. We know that e to the negative x looks like this, and then if you do a negative reflection of that, you're going to get something that looks like that, and then 1 minus e to the negative, 1 minus e to the negative t over RC, that just shifts it up by 1, and as a result, you're going to have a point at 0, 0, and it's going to asymptote towards whatever's in front of the 1 minus e to the negative x. And as a result, for charge, that's going to be C epsilon. But for the voltage drop, that's just going to be epsilon. Now, what does that actually mean? Well, that means after an infinitely long time, the capacitor reaches maximum charge, which is the capacitance times the EMF of the battery, or the voltage of the battery, I should say. But the voltage in the capacitor is actually just the EMF. And when we get to the second part right here, when we discharge the capacitor, that's going to be pretty important. But let's go ahead and take a look at the voltage drop across the resistor. So initially, this resistor right here is experiencing maximum current through the battery. This is the instant the switch is closed at A. So the charges are going to flow, and at time t equals 0, the resistor experiences the maximum current, as I just said. It's just going to experience epsilon over R, which is, by Ohm's law, the maximum current the resistor experiences. However, over time, this current actually decreases because of this capacitor right here. The capacitor is stealing voltage, meaning that the current is effectively getting reduced. Kind of. This charges are being stored in this capacitor, which as a result inhibits the abilities for charges to flow, thereby decreasing the total amount of charge flowing through this, and therefore decreasing the current. I'll say that one more time, just so you're sure. So, as the capacitor gains charges, less charge is actually going to be flowing through this circuit. So as a result, since I is the change in charge over change in time, that means that the current flowing through the resistor decreases. So, as we actually get infinitely far away in time, then what's going to happen is we're going to see that the current is zero. The steady state current in this case is just zero. The capacitor has broken the circuit pretty much. All the charges are just in the capacitor. But yeah. Oh yeah, and this is current as a function of time. And also, here we go. Since voltage R is a function of time, that's epsilon e to the negative t over RC, follows this same curve, follows this curve right here. What this is saying is at time t equals 0, this resistor is experiencing the whole EMF of the battery because the charge doesn't have any voltage drop at time t equals 0. But the resistor, by Kirchhoff's loop rule, has to have all of the voltage drop. But then, again, as time approaches infinity, then the voltage drop is just 0 because the current is 0, so it has to be. But yeah, with that, we pretty much just answered part B through that explanation. The charge in the capacitor after a very long time is C times epsilon, but we're also given values now. So, I'm going to go ahead and just write it in this really small space here. So, the charge after an infinitely long time is going to be C epsilon times 1 minus e to the negative infinity. E to the negative infinity is 0, so it's going to be C epsilon. But what is C epsilon? Well, C is 5 microfarads, which, by the way, is the unit for a typical capacitor you might see. 5 microfarads times the EMF of the battery, which is 60 volts. And as a result, the charge in this capacitor is going to be 300 microcoulombs. The micro carries over, and a farad times a volt is a coulomb, and coulombs are the units for electric charge. And that's it for this part right here. This part, we pretty much focused on charging the capacitor, if you couldn't tell. We increased the charge over time in this capacitor, and we analyzed this circuit and sort of saw the results of how the capacitor and the resistor both affect this circuit. But yeah, that concludes this part on charging the capacitor. Next part, we will see how discharging the capacitor works. We're going to move this switch to point B and see how the capacitor can kind of act as a battery for a little bit, but over time it'll sort of decay in that ability. But yeah, that concludes this video right here, and I hope to see you in the next part.